Today we discuss congruence modulo n, and here we begin with a definition. For natural numbers n, this means integer bigger than or equal to 1, and then x, y, and z. We say x is congruent to y modulo n, and this is written like this. There's 3 bars in this equal sign. X congruent to y mod n, provided, well, we need that n divides x minus y. Now the thing that you will notice, this says that x minus y is a multiple of n. That's exactly this. But when we do proofs, we need to use the definition of divides, right? Now another comment to make. What do we see? Well, this is a relation, certainly, that we definitely see on z, because I'm taking 2 elements in z and I'm telling you what it means for them to be related. So this is a relation on z, and I certainly have much more to say about it than that, but let's do a few examples. (13) is congruent to 1 mod 3, as, well, 13 minus 1 is 12, and 3 divides 12. 18 is congruent to 0 mod 3, as, well, 18 minus 0 is 18, and 3 divides 18. What else can we say? Maybe minus 23. This is congruent to 1 mod 3, as, well, minus 23 minus 1 is equal to minus 24, and 3 divides minus 24. Maybe one more. 5 is congruent to 2 mod 3, as, well, 5 minus 2 is 3, and certainly 3 divides 3. So here are 4 examples. What's something that we have seen which is really congruent? Time, at least in the US. If you are familiar with military time, for instance, you might see 1400, and this is 2 p.m. I'll write this. 1400 is 2 p.m. because 14 is congruent to 2 mod 12. Or similarly, 11 p.m. would be 2300 because of this congruence mod 12. This is really congruence mod 12 when you think about time. Let's prove the following proposition. Given integers a, b, c, and n, a natural number, a is congruent to a mod n. If a is congruent to b mod n, then b is congruent to a mod n. And finally, if a is congruent to b mod n and b is congruent to c mod n, then we get a is congruent to c mod n. So let's prove this now. Okay, well, we will let a, b, c be integers, and then we have some natural number n. For the first one, this holds as a minus a is 0, and n divides 0. In fact, the justification would be n times 0 is 0. 0 is an integer. Okay, that one was quite short. Suppose a is congruent to b mod n. We need to show b is congruent to a mod n. There exists y and z with, well, the definition of this is that a minus b is ny. Then, well, what I want to say is something about b minus a. I want this to be a multiple of n. B minus a is just negative a minus b. So this is negative ny, which is n times minus y. As minus y is an integer, we see that n divides b minus a, meaning that b is congruent to a mod n. And this proves number 2. For number 3, well, we have 2 things to assume here. We suppose a is congruent to b mod n, and b is congruent to c mod n. So then, well, we have 2 integers, say x and y, with, well, we would have a minus b would be nx, and b minus c is ny. Now, if we look what we're trying to prove, we want a minus c to be n times an integer. But if you notice, you can just add these two, a minus b plus b minus c is exactly a minus c. So let's write this down. A minus c is, well, it's a minus b plus b minus c. And this is nx plus ny, which is nx plus y. And so, as x plus y is an integer, we see that n divides a minus c. And this means that a is congruent to c mod n. And this is the end. We have proved 1, 2, and 3. Now, the beauty, well, look at what we have shown. This says congruence mod n is reflexive. 2 says congruence mod n is symmetric. And 3, look, a congruent to b, b congruent to c, middle ones match. We have a congruent to c. 3 says congruence mod n is transitive. So in fact, this proposition shows congruence mod n is an equivalence relation. This is what I just mentioned. Congruence modulo n is an equivalence relation. Now, you might ask, what are the equivalence classes? They should, well, for each n, the classes of this relation should partition the integers. This is what we discussed in the last lesson. So let's look at an example, say with n equals 4. Now, we will figure out the class of 0, class of 1, class of 2, class of 3, and then we will continue as needed. Okay. Well, this comes from our discussion in the last lesson. Certainly, 0 is in this set, and I could go through here and put 1 in this set, and go here, put 2. We know this is the reflexivity of this relation, or any equivalence relation really, that the representative is definitely in its own class. Now, let's fill out some more. Well, 4, because 4 minus 0 is a multiple of 4. 8. 8 minus 0 is a multiple of 4. 12. 12 minus 0 is a multiple of 4, like this. And we can continue. We would have 16, 20, and it would march forward. And then we could back up. Minus 4 minus 4 minus 0 is a multiple of 4. But you see, in this class of 0, we are getting everything that is a multiple of 4. Okay, so we'd have minus 8. We would have minus 12, etc. So here is the class of 0. Now let's move on. The class of 1. Well, we would have 5, because 5 minus 1 is a multiple of 4. We would have 9. Similarly, because 9 minus 1 is a multiple of 4. And then 13, we can, hopefully you can see the pattern, we can just march forward by 4. The next one would be 17, and then we'd have 21, etc. And now we can march in this direction by 4. We'd have -3, and if you want to check, -3 minus 1 is -4, certainly a multiple of 4. -7, -11. Okay. Now for 2. Well, we have seen twice how we can fill out these classes. We just take one element of the class and march forward by 4. This is congruence mod 4. So we should have 6, 10, 14, 18, 22, and -2, -6, -10, like this. Any given one you can check, right? -10 minus 2 is -12, and that's definitely a multiple of 4. Okay, now finally for 3, let's march forward by 4. Like this, and then we march in this direction. This would be the class of 3. Now you could ask yourself, what about we continue, right? Let's try. What happens? What if I say, everybody write out the class of 4? You can say, well, it's already on the board. It's right here. This is also the class of 4. This is just choosing a different representative. Or pick your favorite integer. 17. Find the class of 17. Well, in fact, it's here, okay? This is also the class of 17. This is just picking another representative. So in fact, these are all the distinct classes. There are 4 distinct classes, and it is common in working modulo n to start with 0 and end at n-1 as the chosen representative. That is what's common. So let me erase these. It's not incorrect, it's just not what's commonly used. But you see, this definitely partitions the integers. Even though I don't have every single integer written on the board, that would not be possible. But we can see, for example, just looking at these, they definitely appear disjoint. And then we can start counting. 0, 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12, 13, 14, 15, and marching forward. And similarly, -1, you see they're marching backwards. So you see how we fill out all of the integers with these 4 sets. They are non-empty, and I mentioned they are disjoint. And so this definitely forms a partition of the integers, these classes. And this goes back to what we proved last time about equivalence classes of an equivalence relation. Now for a definition, the set of equivalence classes of the congruence modulo n relation on Z. Well, this set of equivalence classes, this is denoted Z sub n, and this is called the integers modulo n. Okay, it's a set. We just saw Z4, right? Now, as a set, Zn is the class of 0, the class of 1, the class of 2, out to the class of n-1. As I mentioned, these are typically the way that we write the chosen representatives this way. We write with 0 out to n-1. We saw this just as a comment, which was the class of 0, the class of 1, the class of 2, and the class of 3. But we have a Zn for every positive integer n. It's these equivalence classes. Now, we can define addition and multiplication on Zn. These are on classes. We can define addition and multiplication. Well, we have addition and multiplication on integers, this we know, and we can define addition and multiplication on these classes. Let's discuss this now. To define the class of A plus the class of B, this is n, the integers modulo n, or the product, the class of A times the class of B, the only thing that makes sense is we just take the class of A plus B. And similarly here, we take the class of A times B. For example, in Z6, if we take the class of 4 plus the class of 5, and the class of 4 times the class of 5, this would be the class of 9, but we want to represent this as an integer between 0 and 5. So mod 6, this is the class of 3. And similarly, this is the class of 20, but mod 6, this is the class of 2. Now, we could have taken a different representative. So for instance, we can also, and I am doing this right here, we can also represent the class of 4 as the class of 10. And the class of 5, this is the class of 11. We add these two, we get 21, but you notice mod 6, this is also, we get the same class, the class of 3 in both cases. Well, because, say 21 minus 3, this is 18, and 6 divides 18. So what we see in this example, here at least, and we could do the same with multiplication, is that if you choose a different representative and then add, we still get the same underlying class. And this is really needed in order to make addition and multiplication on the equivalence classes well defined. Now, let's prove that. So there is a proposition here that says that this operation and this operation are well defined on the integers modulo n, and then maybe we will look at the multiplication table and addition table for a small n. Okay. What this proposition states, well, we have 4 integers, a, b, c, and d. N is a natural number. If a is congruent to c mod n and b is congruent to d mod n, then a plus b is congruent to c plus d mod n, and ab is congruent to cd mod n. This is telling us, once we prove it, that this addition and multiplication are well defined on classes, because say A and B are my choice of representative, and I add and I get the class, right? And then someone else takes C and D as their choice of representative and they add. Well, this says the class of A plus B equals the class of C plus D. So we get the same element in the integers modulo n. This says the class of AB is the same thing as the class of CD. So you get the same element in the integers modulo n. And this is important, like I mentioned, so that we have this times and plus being well defined on Zn. For the proof, let a, b, c, d be integers and n a natural number. Now, this here we are assuming for both 1 and 2. So we assume a is congruent to c mod n, and that b is congruent to d mod n. Then, well, there exist 2 integers, say x and y and z, with a minus c is in x and b minus d is in y. Now we can begin with part 1 and part 2. So for part 1, we want a plus b to be congruent to c plus d mod n. Well, A plus B minus C plus D. This is, I can just rearrange this. This is A minus C plus B minus D. A minus C is in X. B minus D is in Y. And this is in X plus Y. So as X plus Y is an integer, we see that N divides this. A plus B minus C plus D. And this means A plus B is congruent to C plus D mod N. So far, we have proved this. Number one, we have shown that this addition on classes is well defined. Now let's work with number two. Well, I'm just going to write this a little bit differently. So notice, what do we see? That A is in X plus C, if I add C to both sides, and B is in Y plus D. Now I want to say that AB, the product, is congruent to CD mod N. So I have these two, and let's just multiply. AB, this is NX plus C times NY plus D. And this we can multiply out further. This is N squared XY. Let's see, plus NCY plus, we would have NXD. And then finally plus CD, right? Now we want to say that AB minus CD is a multiple of N, and in fact we have it. If we just subtract AB minus CD, this is N, this would be NXY plus CY plus XD. And then as NXY plus CY plus XD is an integer, we see that, well, AB is congruent to CD mod N. Right, because this here is an integer that says that N divides AB minus CD, and this is the precise definition of AB being congruent to CD mod N. Now let's look at the addition and multiplication tables for Z3. First, let's do addition, and that's here. We are working in Z3 where the elements are the class of 0, the class of 1, and the class of 2. And I will put an entry here which tells you precisely, well, for instance, here would be what is the class of 0 plus the class of 0. Well, 0 plus any number is just that number. 0 plus 2 is 2, 0 plus 1 is 1, and similarly here. And 1 plus 1 is 2, very nice. 1 plus 2 is 3, but we want to represent this as a class where the representative is between 0 and 2. So that would be like this. Now we add 2 and 1, this is 0, and 2 and 2, this is 4, which is 1. Okay, this is the addition table in Z3. Now let's do multiplication here. Well, 0 times anything is 0, and so all of this row and this column is filled with just zeros. And 1 times 1 is 1. 1 times 2 is 2. 1 times 2 is 2. And then we have 2 times 2 is 4, which is the class of 1. So these are our addition and multiplication tables in Z3. Let's see, maybe let's do one more because these are kind of small. We will do Z4, and then this will be the end of today's lesson. Well, I started over here on times. All I did was fill in that 0 times any any integer is 0, and so these classes in this column and this row, just like we saw for Z3, will all be 0. And I can similarly do the same here, that 0 plus any integer is that integer. And so we can quickly fill in the first row and column on this table. Now, 1 plus 1 is 2. 1 plus 2 is 3. 1 plus 3 is 4, which is 0. And now we have 2 plus 1. 2 plus 2 is 4, which is 0. 2 plus 3 is 5, which is 1, mod 4. And now we're on this one. 3 plus 1 is 4, which is 0. 3 plus 2 is 5, which is 1. And 3 plus 3 is 6, which is 2, mod 4. So this is the addition table for Z4. And then we will finish the multiplication table here. Well, 1 times any integer is the integer, and so we get the following. Okay, these 4 are the ones that get interesting. 2 times 2 is 4, which is 0. 2 times 3 is 6. Oh, which is 2. And 2 times 3 here is 6, which is 2, mod 4. And the last one, 3 times 3 is 9. 9 is, well, it's 5, but it's also 1. So we have a 1 here. 9 is 1, mod 4. So this would be the addition and the multiplication table for the integers modulo 4. These are really classes of this equivalence relation.